Hi, everybody, and welcome to Exponentials and Logarithms. Now, this one's coming a little bit out of order. So this video may feel a little bit short because I'm mostly interested in what sort of questions you have in using these formulas, because there's a lot of little nuances here and there throughout them. So just working a bunch of problems for you isn't going to get you very far. Being able to see where you got to do things and asking, should I do this? Should I do that? That's more what you're going to get out of this. So I could work problems all day and you still might not necessarily get these ones. So it's more about being able to catch little differences in them because they just look way too similar to each other. But I'm going to give you at least some so you can get started. But for the most part, we got to work these together because they're weird. Now, one thing that we're going to talk about, it's very similar to the power rule that we first learned. So if we're doing, we're doing a derivative and, no, we're doing a derivative, stupid active inspire crashing on me. So we've got something going on inside of our exponent. Normally it was just like a 2, or no, I'm sorry, it was just like an x, nothing fancy. But if there's something going on in there, if it's like a cotangent to some power, or there was like a 2x plus 3 to some power, we can't really necessarily ignore what's going on inside of the exponent. So if there's something going on inside of there, we also need to multiply by the derivative of the inside. So if there's some funny business going on in there, we need to multiply by the derivative of the inside. Now, technically, we've been doing that up to this point. If we took our derivative of x cubed, we were just saying, oh, that's 3x, come on, pen, 3x squared. And then we would multiply by the derivative of the inside. But the derivative of the inside is 1, so it doesn't really do anything. This is more coming into play when we are doing stuff like 3x squared. Okay, now we get 2 times 3x to the 1 multiplied by the derivative of what's inside of there. Now, really, we could just square the 3, square the x, and then ignore all that nonsense, but we might not always be able to do that. Now, some log and exponent stuff that we're also going to play with today, because that's not quite enough. I mentioned this way back when, but the derivative of e to the x ends up being just e to the x because e is a number of growth. And if you take the derivative of growth, it's that same growth. So it's an interesting property and why mathematicians really, really like e. It's a really cool number. This one is talking about if we have some number to a weird exponent, we're trying to do a derivative of that, then we have to do all of these crazy calculations. We keep it the same. We take the natural log of what was ever on the inside, and then we do the derivative of the exponent. Example of that incoming soon. Here's another goofy one. If you take the derivative of natural log, it ends up being 1 over whatever's on the inside times the derivative on the inside, similar to what's going on in that top uh, derivative rule. Oh. If you are doing a not natural log, because natural log is related to e, so that one worked out really nicely. But if you're not doing natural log, then it gets a little gross, and so we get some extra stuff. Technically, that extra stuff does show up in the natural log one, but if you're doing the natural log of e, it's just 1. So ln of e, because that's the base of natural log, would just go away. Mostly, I just want you to have those rules. That's just a quick mini proof of each one. All right, so say we're doing this derivative. So we've got e to the x squared. So unfortunately, I know I just said that the derivative of e to the x is just e to the x. That's not what we have. We have e to the x squared. So, dang, what are we going to do? What we're going to do is we're going to try to cheat just a little bit. We're going to use that idea of u. So that is sort of our inside bit, u. I'm going to let u equal x squared. And then we can replace what's going on in this function. So it's y equals e to the u. Okay, well then that's easy. So dy dx, so our derivative, dy or dx, which is just a fancy way of writing derivative, is going to be e to the u, but then we need to multiply for whatever that goofy exponent is. What is u prime? Okay, well u prime, derivative of x squared is 2x. Okay, so that is just 2x. So we'll put it back in. So e to the u, which was x squared, times our 2x. If we wanted to write that all nice and neat, we would probably write 2x first, followed by our e to the x squared. And that is our derivative. See how it's kind of goofy? All right, let's try another one. So here we've got that other one, that one that was like a to the u. So our u in this case is cotangent of x. All right. So our property for this one was saying if like you have, our property is going to say that our dy dx, our derivative is going to be 3 to whatever u is, because our 3 is acting as that a in that rule. Hopefully you've got it written just a little bit above your paper. I've got it over to the side here with me. 3 to the u times the ln. Can you be out of the way? Ln of a, and in this case our a is 3, times the derivative of u prime. What's the derivative of u? Okay, all right, well now we can just put all that stuff back. Well, we can put u back. So we get 3 to the cotangent of x times our natural log of 3 times whatever the derivative of cotangent is. So our derivative of cotangent, that was back in our trigonometric notes. We took a note down, we wrote that down. What was the cotangent of x? Well, I've got it right over here. It's negative cosecant squared x. You can check your notes to make sure you've got that. So negative CSC squared x. Now this is going to be a gross one to try to write neatly. I mean, I want to put that negative first. So negative 3 cotangent of x. And then, I don't know, let's put the ln to kind of break up the cotangents. There's not a nice, neat way to write this one. It's just kind of gross looking, but that's kind of it. There's a lot of stuff in there. Yeah. Let's try another. See what I mean? Where it's just like, well, there's all kinds of these goofy little bits. All right, we got a natural log one, and I want to try to find the derivative of this thing. So there's something that's going on the inside, trying to find that inside bit. So in this case, the inside bit seems to be the ln of x. Ooh, so that's going to be our u. All right. So we're going to say that y equals u squared. So to find the derivative, dy dx is going to be, well, we got to do the 2 u to the 1 now, times the other thing, times whatever the derivative of u is. Sorry, my brain stopped for a second there. Well, I got to figure out what the derivative of u is. So what's u prime? So ln of x, we wrote that one down earlier. Ooh, that was the really neat one. It is just 1 over x times the derivative of whatever's inside of ln, but I mean, it's just an x this time. The derivative of x is just 1, so it's just 1 over x. All right, so let's put those pieces back in. So that's just a u to the 1. That's not a prime. I don't have to do u prime, u prime. So we've got 2 times our ln of x times our u prime, which is 1 over x. So if we wanted to write this neatly, we could put that x in the denominator underneath those. Like that. All right. Let's try another one. Oh my gosh, you know what this one needs? This one needs product rule because we got two things multiplied together. We don't have any sort of like thing inside of thing for this one. We do have a whole bunch of pieces that we've got to deal with. So this one, I can jump right into dy dx. I don't have to do that u thing. So dy dx, the derivative of x is just going to be 1 times the second thing, ln of x. Product rule tells me to put a plus in between them. Do the first thing, which is x, times the derivative of the second thing. So the derivative of ln. The derivative of ln we wrote down earlier as 1 over x. Minus, in a very separate fashion, I need to do the derivative of x is 1. Great. All right, now we just got to clean this up. So 1 times the ln of x, that's just the ln of x, plus x times 1 over x. Well, that's 1. Minus a 1. 1 minus 1, oh, that's 0. So this whole thing just equals the ln of x. That's our derivative. Oh, neat. Couple more. So I'm going to find f prime of x. This time they're also saying like, hey, you should probably double check that domain and make sure there's nothing goofy going on with that, because there is going to be stuff goofy going on with that. Okay, but we'll wait for that in the end. Let's start by looking at, okay, what's our sort of inside bit? Our sort of inside bit going on right here is that 2x plus 2. So we need to worry about that as our u thing. I'm double checking to make sure I've got my key going. So let's see, u equals 2x plus 2. And you know what, I'm just going to do it right now. Let's just find the derivative of u. So let's see, the derivative of u is going to be derivative of 2x, that's 2. And the derivative of 2 is 0. So u prime is just going to be 2. So when I find f of x, or f prime of x, when I find the derivative, I need to do 1 over what was ever inside of that natural logarithm. So that's 2x plus 2. Multiplied by whatever the derivative of that inside was. Well, the derivative of the inside was 2, so I need to multiply this whole thing by 2. So that equals 2 over 2x plus 2. Ooh, I could factor out a 2 from the denominator and simplify that a little bit. So then I get the derivative as 1 over x plus 1. So that's f prime. Now it said, hey, worry about what's going on with our domain. Yeah, we got to look around and see what's going on with our domain of this thing. Ooh, right here. It would be really bad if we put -1 there. That would be bad news bears. Now, wouldn't it? Yeah, we don't want that to be -1. That'd be 0 in the denominator. No good. So that's a restriction on our domain. But remember, this thing came from this piece over here. So that 2x plus 2, we need to make sure that that stays greater than 0, because we can't put negatives into logarithms and we can't put 0 into our logarithms. So we want to make sure 2x plus 2 stays greater than 0. So that means x has to be greater than -1. And so if we combine those two ideas together, can't be -1, it's got to be greater than -1. Really, all we're saying for our domain is, hey, it's got to be greater than -1. And the reason that we're doing that is it's being taken from our original function where we couldn't put those like -2's into that natural logarithm. And when you find derivatives, if you think back to our original definition of derivatives, we were evaluating f at certain things in order to find the derivative. So if we can't evaluate f at x equaling 2, at x equaling -2, then we can't do that. If we can't do it in f of x, we certainly can't do it in f prime of x, because we need f of x in order to find f prime. Even though I didn't do any of those fancy old versions, like think about back at the beginning of this chapter when we were finding derivatives. Think about that way. If we were doing it that way to find the derivative, I wouldn't be able to do that, because I can't put -2 into that natural logarithm. That's why these kind of domain restrictions carry over. Let's do one more of these, and I think that is going to be it. Because again, I want to see your own personal questions about what's going on with these functions, because this is also a type that we haven't done yet too. So our inside bit here is our sort of u thing. So u is going to equal x plus 1. And you know what? It's more than just that. Now that I look at that again, it's more than just that x plus 1, because really our bigger thing that's going on is that whole like square root inside of a logarithm. Oh, that's our crazy u thing. So it's really that x to the 1/2. So u prime is going to be 1/2 x plus 1 to the negative 1/2. I would have to do the derivative of the inside on that thing too. Oh, but wait, the derivative of x plus 1, that's just going to be 1. So I don't have to worry about that. Oh, phew. If that had been like a 2x plus 1, then I would have had to tack that on too, but it wasn't there. So see what I mean? Like, if I could like work all kinds of examples, but we kind of need to see specific ones that are doing that. All right. But anyway, let's keep going. I got to figure out what f prime of x is. And we have to do this fancy new logarithm to goofy bases version. So I need this 10. I'm going to put that into a natural log in just a bit. But our derivative is going to be a whole bunch of stuff. It's going to be 1 over whatever was inside of our function. So I'm just going to jump right to it. It's this x plus 1. It's that whatever was inside of our logarithm, not natural logarithm. Then we always have an ln right here, and it's the base of the logarithm that we started with. It was, in this case, 10. It's log base a in the example. Then we need to multiply this whole thing by u prime, the derivative of what was inside of the logarithm. Okay, let's write some of this stuff out. So I'm going to put that ln first. I just like that first. ln of, no, actually, I think I like it better where it was. Sorry. Square root of x plus 1, ln of 10, times we got to do u prime. And I don't like that it's like a negative exponent, so let's make it a positive exponent by putting it in the denominator. So that's 1/2 square root x plus 1. Okay. Ooh, look. This is being multiplied by itself because this is being one big fraction thing. So that thing is being multiplied by itself. Those square roots are going to undo each other. We'll square our square roots. Oh, sweet. So we are going to have, I'm going to put that 2 first. That x square root of x plus 1 times the other square root of x plus 1 becomes just a regular x plus 1 and an ln of 10. And I think that's about as simple as we're going to get that thing. Yeah, that seems pretty good. All right, now we need to identify what are our domain restrictions. So right here, I can definitely say that -1 would be bad, because if we put a -1, that would make that whole denominator equal to 0. Just looking at f prime, that doesn't tell me the whole story. I need to look back at this piece. Inside of that square root needs to be It has to be greater than or equal to 0. And on top of that, it's inside of a logarithm. So since it's inside of a logarithm, it can't be 0 either. So we don't even want equal to 0. We want to make sure that x plus 1 stays greater than 0. So that's really saying x has to be greater than -1. So just like before, this is telling us more restrictions than this, and we need to be as restrictive as possible. Never ignore restrictions. So we want both restrictions happy, and we'll make both restrictions happy if we keep x greater than -1 for our domain. So there is our f prime of x. Whoop. And in the little blue box, that's our domain. Huzzah! So those are all those rules. So I believe I've given you an example of all 4 of those, including that first one a few times. What we need to do is we need to work some more together, but I really want you to take those steps and work through these problems on your own so that you can have that experience of identifying, okay, well, what's the inside, what's the outside, what's going on? If I just keep telling you what's inside and what's outside, you're not going to quite get it. So you need to be practicing with me or on your own and just seeing how they work out. All right. So I'll see you in class. Make sure you come with lots of questions.